This is the challenge problem from the Unit 2 review. We have two polynomial functions, degree n. So we don't have a specific number, but that's okay. We basically just say we've got polynomials. So whenever a math problem generalizes something, so it's not something explicit, because I could have given like a cubic here and a cubic or a quartic or a quadratic, but I don't do that. And so whenever a math problem does that, you always got to be aware in the problem solving process what details are actually important to the solution. So the very fact that this is generalized to just n, some number, as long as that's a positive integer, that's your first clue that that's probably not the crux of the solution. So if the specific degree of this polynomial isn't really what matters, then the overall question behavior, the kind of problem solving you'll be doing, isn't going to be tied down to, oh, I need to be thinking about how quadratics work or how cubics work. It'll just be, okay, how do polynomials behave in general? So we got two of those polynomials. And just as a point of notation, because this is the first time really that notation gets a little bit more general, is that each one of these A's, and notice that they got these we call it an index. So the indices, so the 1, 0, 1, 2, and then we have these dots to indicate that the pattern goes on until you reach up to n. So we often implement that in mathematics to denote large sequences of constants that are different numbers. They could be different numbers, but we want them to be understood conceptually as associated to the same thing. In other words, we don't want to have it be a plus bx plus cx squared, etc., because all those different letters will get confusing. We want it to correspond to just the function f. And so constants of the form a sub I, that's what this means right here. So a sub I, where the I is representing the index. If it's one of those, if we use a symbol like that, it's going to correspond to f. And the reason we do that is to distinguish it with the b's. So we have the same number of constants b, but we want them to be understood to be coefficients not of the f function, but of the g function, because we do want them to be distinct from each other. We don't want to accidentally restrict our constants to mean the same exact thing. So you can't recycle your variables. I couldn't put a's down here. And if I did that, then I basically just copied the function over. So there's no reason to make a new function. So that's what the notation really is going on here. We've got that a sub I and the b sub j, essentially describing these are the families of all of these constants to distinguish between two functions. So we have two distinct functions. Each of them are polynomials. They've got their own different coefficients and such. This is going to do something we call preserve generality. And in some textbooks, you'll see there's always mention of doing certain things in a problem or in a solution to prevent something we call loss of generality. So that's a little bit of a tidbit there. So that's why this is more of a challenge problem, because all the problems in the unit haven't been super abstract. They've been more applicationary, where this is now slightly more abstract, where we've got, these different constants. We don't even state the degree exactly. And so we're avoiding any loss of generality when talking about an n-degree polynomial function, and then we have two of them. So, and a few more things on the notation. So right here, n comma m, the comma is the word and in mathematics. And then the symbol here, we already talked about this, but it's always good to review. In, or is a member of. And then a double struck Z by itself would be the set of integers. So I'll first say integers. But then notice there's a superscript here. So this plus, whenever you put a plus there, it's pretty intuitive. That means positive. So we only want the positive integers. We don't care about negatives or zero. Now this colon right here, a colon, I like to think about it as the word such that. When I write that, when I write it I would say such that when I make these two dots. And then that's a condition. So such that. And then here's the condition, n is equal to n. So this is how you want to read math. When you see this string of symbols right here, that's really communicating, if I were going to say it in English, I guess, two positive integers such that n is equal to m. That's all that means. Does it seem a little bit redundant? Perhaps. But the reason why we have to state this, because if they're the same number, the reason we got to distinguish between them is because we need these to be the same. We need them to be n-degree polynomials. Okay. To address the question, why on earth would we put an m here instead of just simply doing it to n again? We could have done that. The reason why it's done like this is to really emphasize more conceptually that we want f and g to be unique functions. We don't want to confuse them as the same. Now, of course, you could just replace the n here with an n, and it would actually work. But I wanted to avoid confusion, essentially, over the difference between the two functions. So that's the only reason why this is here, is just to essentially show that n and m are the same size so that you have the same degree for both functions. So then after all that, we have, I should just use my erasing tool. Bam, okay. Then ultimately our goal is to find this limit, and it's going to be a quotient. So we're going to have the function f over the function g. Here's something in general that's good to know for math language and as you go in calculus in general, is if you have a ratio of polynomials, we call that a rational function. And I wish I knew the historically correct version or a reason for this. It's slipping me right now. Could be due to the fact that if you had integers, ratios, like a rational number is a ratio of integers. But essentially, if you got a polynomial divided by a polynomial, common example, like x plus 2 over x squared minus 3. So this would be rational because you got a polynomial in both the numerator and the denominator. So rational functions are a pretty big deal in calculus, actually just mathematics in general. And so you notice here that we're taking a limit of a rational function because f and g, that's forming the quotient, and we know that f and g are polynomials. So let me put the limit right here. So we got the limit as x is approaching infinity. So immediately in my brain, I'm thinking, okay, this is a limit approaching. We're looking at what happens when x is approaching infinity. So again, infinity is not a number. It's an idea. It's this idea of unboundedness in that rightward direction on the Cartesian plane. And so I understand immediately that when I'm trying to evaluate this limit, I'm thinking of end behavior. I'm thinking of the way this thing is going to trend and behave as I unboundedly increase to the right, instead of plugging in some sort of a value and then trying to compute something. So different limits have different kinds of strategies, and especially with an infinite limit, the mental mode you should switch into is more conceptual and behavioral rather than computational, as in with like if you just had a continuous function and you were approaching a specific point. So let's plug in what f actually is. So f of x is the polynomial a0 plus a1x plus a2x squared, etc. And we have up to the nth term. And then g of x is b0, b1x, b2x squared, so on and so forth. We have the same number of terms. That's what's important, is that since n is equal to m, I can substitute in the n here. And now in both the numerator and the denominator, we have the same degree. So we might not have the same number of terms, right? Because some of these constants could be the number 0. So there's nothing stopping us from setting like a2 equal to 0, for example. And so that would eliminate him. And it technically wouldn't be a unique term up there. But the degree is the same. The degree is n in both the numerator and the denominator. And so when we're taking this limit, as x approaches infinity, whenever you have this ratio, you're really kind of looking at what I call a running race in mathematics. Who is going to outpace the other guy first? Is it going to be the numerator that's going to win the race and just outpace him as you go to infinity and it's going to blow up to infinity? Or maybe the denominator is going to outpace. And in that case, then now the denominator, you're dividing by something that's growing faster. And so now you're going to slam into, the axis, the y-axis. You're going to hit 0, or sorry, the x-axis. But what happens if they're the same? Well, what happens if they're growing at exactly the same speed? And that's the key concept here, is that we were very insistent on the degree of the polynomials being the same. And since we have it defined as such, that means the speed at which the polynomial is going to grow in its end behavior to the right, it's the same. And so the only difference really is going to come down to that constant that's being multiplied by it. So let us, and we also take a note that b sub n here is non-zero. Because if this was 0, then this would no longer be the degree. I think, so that's something that isn't explicitly stated, but can go under the radar because it's a little sneaky. So we don't have to worry about division by 0, because b sub n, it's impossible for b sub n to be 0. Because if b sub n were 0, you would have 0 times x to the n. Well, that's just 0. So that means the next greatest term would be bn minus 1 times x to the n minus 1. But we just said that the degree of the polynomial is n, and this would be the degree is n minus 1. Those are different things. So that's a contradiction. So that's why we can't have b sub n equal to 0, in case that was ever a miscellaneous concern in the thought process. So now what we're going to do is whenever we have a rational function like this, the common strategy is to divide everything. So in the numerator and the denominator by the highest power from the denominator function. So in this case, it doesn't really matter, but we're going to divide by n because n is the degree of the denominator. So divide everything by x to the n, and I'll scroll down for this. And that's going to give us the limit as x approaches infinity of now, so a sub 0 over x to the n plus a1. Now, we have x, and then we're dividing it by x to the n. So really what's going on here, I might actually write it. This will be less ugly to write it. We'll have a1 x to the 1 minus n, because we have a power, the 1, and then we're subtracting n from the exponent, because that's the same thing as dividing by x to the n. Plus, and then the pattern will continue, because a2, x to the 2 minus n, and this will go on and on and on, until we get to a sub n times x to the n minus n. All over b, and then it's going to be repeated pattern. So notationally, it'll look similar, but funnily enough, it's really the notation that's the most difficult part about this challenge problem, because it's the first time you kind of have to accommodate, how do I properly represent these general sums, this general polynomial correctly? So this is how you do it. Oops, I almost looked like an M there. Okay. And now n minus n is 0, and we know that x to the 0 is just 1. So we can replace this with the number 1. And we can replace this with the number 1. So that's just a sub n at the end and b sub n at the end. And now what happens is we're going to use our limit properties. So I'll be careful to practice the things that I've been actually teaching you in the text. I'll scroll not so far the wheel. So one of those limit properties is that the limit of the quotient is also the quotient of the limits. In other words, I can take the limit in the numerator here. Wow. Okay, the limit as x approaches infinity of a sub 0 over x to the n plus a sub 1, x to the 1 minus n, a sub 2, x to the 2 minus n, so on and so forth. And then we'll just write down a sub n, simplify that. We don't include the times 1. And the denominator is going to look essentially identical. We'll just replace the a's with b's. So x approaches infinity, b naught over x to the n, b1, x to the 1 minus n, b2, x to the 2 minus n, and then as many times, as needed to get to the nth term, so b sub n. And then when we actually compute this, we're going to note that, first of all, I'll make an aside, because this is the core concept here, is from the graph of the inverse function. So this is the graph of 1 over x, is that we know that the limit as x approaches infinity, well, really, this is a constant, so k over x, of a constant over x, that approaches 0. And so notice here we've got a constant over something that's blowing up to infinity. And whenever you have something constant in the numerator and then the denominator is approaching infinity, well, we see from this, it's going to behave towards 0. So this is going to trend to 0. Now, in a similar way, we got a sub 1 times x to the 1 minus n. Now, we know something special about the number n. The number n is the degree of the polynomial. And the degree of a polynomial, by definition, that is the largest exponent. So, or rather, the largest power in your polynomial. So, n is the largest power, and 1 is most definitely not the degree. So, 1 minus the degree is going to be a number that's negative. N is greater than 1. So, subtracting that number from 1 is going to get you underneath 0. Granted, we don't know exactly what number that is because, remember, this is more general, but that's irrelevant. All that we need to know is that that exponent is going to end up being a negative exponent on this particular x. And because it's a negative exponent, that's the same thing as dividing by x to the something. And that x to the something, very similar to this, is going to go to 0 as you approach infinity. So this also goes to 0. And I think now, after talking through those two, it's pretty easy to see how the dominoes fall. Because then, well, sure, we have 2 minus n, but n is still the degree. And the degree will still be bigger than one of the intermediate powers. And so you'll have a negative exponent, throw the x in the denominator to some power, which will go to which will blow up to infinity. And then you have infinity behavior in the denominator with a constant in the numerator, so that'll also go to 0. Now notice that there's no x associated with that. That's just a constant. So the constant is not going to be changed. So that'll stay there. But every single other term leading up is going to go to 0, et cetera, et cetera. And the same thing is going to happen in the denominator. So for analogous reasoning, these are all going to 0 as well. And so all these intermediate things are going to go to 0. So all that's left is the term that doesn't get blasted away by something, by the x's going to infinity. So the aftermath of simplification is that we have a sub n over b sub n. And that's it. So what happens is, I guess I can say this is the final answer. So then the limit as x approaches infinity of f over g is a sub n over b sub n. And since n is equal to m, we could say a sub n over b sub n. And we would answer like this to preserve how the original question statement posed our stuff over here. So in other words, here's the takeaway. This is what this exercise really does without you maybe noticing it. This is how you can prove that the limit as x approaches infinity of a ratio of polynomials will be simply this. If they have the same degree, then the answer is going to be the ratio of the coefficients to the one with the degree. So it's like to the a sub n x to the n. So here's how we can apply this result is if you really understand this exercise, then you can solve some of these limits really quickly because you've done all the hard work. So limit as x approaches infinity of say x cubed plus 2x minus 1 over x, let's do 4x cubed minus 6x squared. If you were given this limit, all you have to do is say, okay, well, the numerator is a polynomial, and the denominator is also a polynomial. Now, the degree of the polynomials is shared. We have the shared degree of 3. And I know that if I do this, no matter what degree that is going to be, I simply end up with the ratio of the coefficients. So the coefficient to this one is 1. So we'll have a 1. And the coefficient here is 4. So it's 1/4. And you're done. That's how fast it is. So that's why I like this challenge problem, because in one sense, when you really do understand what's going on, you really unlock a whole bunch of fast limits dealing with infinity, especially with these rational functions.
Oh, sorry. I have a question. How did you deduce that the coefficient for the denominator was 4? Wouldn't it be 2 or 2 or yeah, 2 because you're factoring out both, like the 2 from the 4 and the 2 from the 6. You can't factor out like, or maybe I'm misunderstanding how you did that.
Oh, no, that's a good question. When you're looking at the polynomial in its expanded form, so basically coefficient with each power, you don't do factoring, because then factoring, that would be the factored form of it, and so it wouldn't be the polynomial listed out term by term. So I wouldn't consider 2 to be the coefficient of x cubed, because factoring is just going to lead me to 2 times x cubed minus 3x squared. But I wouldn't say that 2 is the true coefficient here of x cubed because I haven't distributed yet, if that makes sense. So
Yeah, it does.
so that's why we don't that's why in this case the coefficient's 4. It's just whatever the standing next to the number. So yeah, that's the challenge problem. That's why we do the challenge problem, is so that you can unlock this little trick, this limit trick. Basically, doing the whole exercise in full kind of lets you take the shortcut whenever you see an easy rational limit as such.